All right, Chapter 7, Section 3, the law of cosines. This section we'll be looking at two different cases for solving oblique triangles. First, we'll be looking at the case where two sides and the included angle is given. And finally, we'll be looking at the case where three sides of the triangle are given. For both of these cases, a unique triangle can be formed, okay? A unique triangle can be determined. We'll start this section by deriving the law of cosines. Let's start with an oblique triangle. Remember, an oblique triangle is a triangle that does not have a right angle. And let's choose an oblique triangle, triangle ABC, like in the diagram, where vertex B is located at the origin of our plane. And side BC is on the positive x-axis. The coordinates at vertex A here are x comma y in the plane. Okay? Now I want us to drop the perpendicular from vertex A down to the negative x-axis here. And what we're about to say next is true when it comes to vertex B for angle B, whether angle B is obtuse or acute. And the following is true. Sine of angle B would be y over c, remember opposite over hypotenuse, and cosine of angle B will be adjacent, x over c, adjacent over hypotenuse. The following two statements would lead us to y is equal to c times sine of angle B. Over here, we would get that x is equal to c times cosine of angle B. So what we're about to do right now is to substitute this value of x and this value of y in for the coordinates at vertex A. So instead of this point having coordinates x comma y, we can say that it has coordinates c cosine b comma c sine b. So I went ahead and just said that coordinate x is c cosine b and y is c sine b. All right, now what we can do is use a distance formula to write an equation for side B, or if you like, side AC. The distance formula can be written as B is equal to the square root of the sum of the squares of c cosine b minus a and c sine b minus 0. Remember, that is to say this x coordinate minus this x coordinate, and then that y coordinate minus that y coordinate, right? Which in this case is c cosine b minus a, quantity squared, plus c sine b minus 0, quantity squared. And of course, the square root of all of that. What we can do at this point is we can square both sides to get rid of the square root. And at the same time, let's consider expanding both of these squares, okay? All right, when we expanded this binomial here, the square of this binomial, we get c squared times cosine squared of b, right? And then minus 2 times a times c cosine b, and then plus a squared, and then here it's just c squared sine squared b. Now, what I want you to notice is that, let's see, that this term here has cosine squared b, this has sine squared b, and that's an identity, a Pythagorean identity. So what I'm thinking about doing is factoring out the common factor of c squared. That leaves me with cosine squared b plus sine squared b, and then I can use my identity to simplify. So the left-hand side is still b squared. I'm going to use the associative property for addition to write a squared first on this right-hand side, plus, now watch this, I'm going to factor out c squared from both this term and from this term, which would leave me with cosine squared of b plus sine squared of b, like that. And then, of course, we have minus 2ac cosine of angle B. And now this here, I'll underline it for us. This is an identity. This is equal to 1. So that simplifies this to b squared is equal to a squared plus c squared times 1 minus 2 times ac cosine b. So to simplify this just a little bit further, b squared is equal to a squared plus c squared minus 2ac times cosine of angle b. What we got here is just one of 3 forms of the law of cosines. We could have gotten alternative forms had we just placed vertex A or vertex C at the origin of our plane. So according to the law of cosines, it is saying that the square of this side, B, the square of that side of the triangle is equal to the sum of the squares of the other 2 sides minus 2 times the product of those 2 sides and cosine of the angle that's included between them. Angle B is included within those sides A and C. Okay? So here's all 3 versions of the law of cosines. The first is a squared is equal to b squared plus c squared minus 2bc cosine A. Notice that angle A is included within those 2 sides. Here, angle B is included within the 2 sides A and C, and angle C is included within the 2 sides A and B. I wanted you to notice something. If the angle here is 90 degrees, if C is 90 degrees, watch what happens. Cosine of 90 degrees is 0, and so this whole term goes away, and all you would be left with is c squared is equal to a squared plus b squared. Pythagorean theorem. Pretty cool, huh? Here I've also given you what the law of cosine says in words as well, just in case that's helpful. Okay, I think we're ready now to look at our first example. All right, first example, 2 boats leave a harbor at the same time, traveling on courses that make an angle of 82 degrees and 20 minutes between them. When the slower boat has traveled 62.5 kilometers, the faster one has traveled 79.4 kilometers. At that time, what is the distance between the boats? Let's draw a rough sketch of what's going on. All right, everybody, this is the quick sketch that I made. This is harbor, or the departure point. Two boats are leaving. The slow boat is over there. The fast boat is here. 82 degrees and 20 minutes is between them. 62.5 kilometers for the first boat, 79.4 kilometers for the faster boat. This is the unknown, the distance between the 2 boats. We can use the law of cosines here because notice what is given. A side length, the angle between the 2, so 2 side lengths and the angle included within them. So this case is SAS. That's what this is, okay? This is an SAS case where 2 sides are given of the triangle and the angle included within them. All right, so we can use the law of cosines to say that this side, squared must be equal to the square of the other 2 sides minus twice the product of those 2 sides and cosine of the angle included within them. In other words, like this. So this is what we have. X squared is equal to all of this. This is by the law of cosines. And what we can do is we can evaluate all of this on the right-hand side using our calculator. Be careful about inputting 82 degrees in 20 minutes. I can input, I'm sure you can too, degrees and minutes straight into my calculator. But remember, 20 minutes is decimal degrees. You can also divide 20 by 60 to get that decimal portion. Either way, we should evaluate all of this right-hand side using our calculator and then take the square root of all of it. And how many significant digits do we have in this problem? You'll find that we have 3 significant digits, so that's what we want to round to. All right, everybody, I'm getting x squared is approximately equal to 8886.519401. So what I want to do is take the square root of both sides. And to 3 significant digits, I get 94.3 kilometers. This is the distance between the 2 boats at that time. Okay, so that's your final answer. Pretty cool, no? Let's go to the second example. All right, solve triangle ABC. If angle B is 73.5 degrees and side A is 28.2 feet and side C is 46.7 feet. Okay, I believe we can use the law of cosines here and to find our unknown. The only side that is missing is side B, and so we can set up the law of cosines and find side B, like this. So we can use the law of cosines to set it up this way, with our missing side B, starting this all out, and I plugged in everything that they gave me for sides A, side C, and for angle B. And of course, just like before, we want to plug all this into our calculator and then take the square root of both sides, okay? And we have 3 significant digits. All right, I'm getting b squared is about 2228.067664. Rounded, and then take the square root of both sides, of course. So let's take the square root of my answer, and I'm getting that b is about 47.2 feet. Feet is the units there. So there's my missing side. Cool deal. All right, what I'll do last to wrap this up is use the law of sines to find an angle that we're missing. We're missing both angles A and angle C. And between the two unknown angles, let's see, angle A and angle C. The angle that will be smaller between these two will be angle A, because the side opposite angle A is smaller than the side that's opposite angle C. So I'm going to go for angle A first, everybody. Let's go use the law of sines to find angle A. The law of sine gives us sine of angle A over A is equal to sine of angle B over B, which of course leads us to that sine of angle A is equal to A times sine of angle B over, over B, let me move this up a little bit for us, over side B. Cool. That is to say that angle A will be equal to inverse sine of A times sine of angle B over B, right, everybody? So then A is approximately equal to inverse sine of, now, A was given to you. A is 28.2. Sine of angle B, and B was given to 73.5 degrees. Don't forget to divide this by side B, which was given, or actually it was not. We found it, 47.2 feet. Okay, let's punch all this into the calculator. Okay, everybody, and of course, rounding it to 3 significant digits, I get 34.9 degrees for angle A. Cool. I have all the 3 sides. I have angle A. The only thing that is missing is angle C. But you know what we can do? Remember that the 3 angles within any triangle must sum to 180 degrees. So what we can do is angle C, the remaining angle, would be equal to 180 degrees minus given angle B minus derived angle A. So then angle C would be 180 degrees minus 73.5 degrees, that's B, minus 34.9 degrees. So then angle C is going to be equal to 71.6 degrees. Pretty cool, right? We solved this triangle. Alrighty, cool. All right, solve triangle ABC if these 3 sides are given. Okay, everybody, first I want us to realize that we are in this case SSS. All 3 sides are given. The 3 angles, of course, are not given. Okay, let's go find our angles. Let's use the law of cosines. Which is going to be the largest angle? Angle C, that's right, because it's the side opposite angle C. Which is side C, is the largest side. So let's start there. Let's find the largest angle first, angle C. All right, we have c squared is equal to a squared plus b squared minus 2ab times cosine of angle C. Now, I know all the side lengths here. What I do not know is angle C. So I have plugged everything in, and what I'll do is I'll isolate cosine of C. Okay, isolate that. Okay, guys, this is what I'm getting when I isolate cosine of C is equal to 25.4 quantity squared plus 42.8 quantity squared minus 59.3 quantity squared. Notice the signs change, and that's because we divided both sides by that negative as well. And then all of this divided by 2 times the product of those two sides, okay? And so what we're going to do here is we're going to take inverse cosine of both sides to find out what C is. And by the way, folks, if this whole expression, when I plug it into the calculator, is negative, I'll know that angle C is obtuse because of, I know that obtuse angles that terminate in quadrant 2 will have a negative cosine value. Remember, all students take calculus, the signs of our 6 trig functions. If this turns out to be positive, I know angle C is acute, and it's in quadrant 1. Okay, guys, I'm getting cosine of angle C is about negative 0.4780939495. So this is negative, so I know that angle C is going to end up being acute. I'm going to take inverse cosine of both sides, and I'm getting that C is about 118.6 degrees. All right, so cool. So this is angle C. Now what I need are the other two sides. What I can do is use the law of sines to find another angle. Let's go for, I don't know, let's go for, we found the largest angle first. Let's find the medium size value angle next, which would be angle B. Let's find that using the law of sines. Okay, this is sine of angle B over side B is equal to sine of angle C over side C. All right, so then that would mean that sine of angle B is equal to 42.8 times sine of 118.6 degrees over 59.3. Okay? So I'm getting sine of angle B is about 0.633687544. Let's take inverse sine of both sides. And we're getting that angle B is about 39.3 degrees. Cool. The only angle that is left is angle A, and we can find angle A by just subtracting angles C and B from 180 degrees. So then angle A would be equal to 22.1 degrees when you do that. All right, we've solved the triangle. Good job, you guys. I wanted to make sure I give you kind of a summary of what we've talked about so far for solving oblique triangles, because we're pretty much done at this point. We have 4 cases, and so here is case number 1. This is what we looked at in 7.1, when you have one side given and 2 angles are known, or 2 angles and the side included within the 2 angles, and then these are the steps you would follow. In 7.2, we looked at this case where you are given 2 sides and 1 angle. This angle is not included within the 2 sides. And then in this section here, chapter 7, section 3, in this video, we looked at the last 2 cases, SAS, 2 sides and the angle included within the 2 sides, and then the 3 sides given here. And so you have all of the steps that you would follow. So I wanted to make sure you have this for your notes. So I think this is really helpful. Okay, the last thing we want to talk about in this section is Heron's area formula. This is Heron's area formula. So this is a formula for the area of a triangle. I know we have the traditional formula, A is equal to 1/2 times the base times the height. And then we also derived a new formula for the area of a triangle. And we did that in, I believe, the first section of chapter 7. And then this is another formula for the area of a triangle. And this formula is dependent upon knowing the 3 sides of the triangle. So this is really great because you and I can find the area of any triangle as long as we know the 3 side lengths. We don't need the height of the triangle. We don't need any angle measures. This is Heron's area formula. The area of the triangle will be equal to the square root of S times the difference of S and A times the difference of S and B times the difference of S and C. That's Heron's formula, where S is the semiperimeter, which is basically 1/2 of the sum of the 3 sides, the semiperimeter. And of course, A, B, and C are the 3 sides of the triangle. Okay, so basically, according to Heron's formula, the area of a triangle is the square root of the product of 4 factors: the semiperimeter minus the first side, the semiperimeter minus the second side, and the semiperimeter minus the third side. Here's the last example from this section. The distance from Chicago to St. Louis is 262 miles. From St. Louis to New Orleans is 599 miles. And from New Orleans to Chicago is 834 miles. What is the area of the triangular region having these 3 cities as vertices? Okay, in order to use Heron's formula here, the first thing we need to figure out is what S is. S is the semiperimeter. S is half of the perimeter. So it's half of the sum of 262 plus 599 plus 834. Right? Let's move this up. Okay. So then S is equal to 847.5. We're going to be using this value in our formula. All right, cool. Now let's go for it. I think we're ready. Okay, you guys, this is the formula, Heron's formula. It's a square root of this of 4 different factors. The first factor is the semiperimeter, and then the semiperimeter minus the first side, semiperimeter minus the second side, semiperimeter minus the third side. Okay, obviously we're going to punch all this into the calculator, and when we're done, we want to round our answer to 3 significant digits, and don't forget to use squared units. In this case, squared miles. Okay, when you're done, I'm hoping that you're getting that A is about 40,800 squared miles. Isn't that great? We used Heron's formula. We did not need an angle measure. We didn't need the height of the triangle or anything like that. There is a really, really amazing proof of Heron's formula, or the derivation of it. It's in your book on pages 317 through 319, okay? So I encourage you to go look through it. It's really, really, really fascinating, so you can see where this formula comes from. That would be really great. This is the end of this lesson, 7.3, the law of cosines, and the end of us kind of solving oblique triangles. I'll catch you in the next video, which will be entitled 7.4, and we're going to be talking about vectors and how they're geometrically defined. All right, everybody, I'll catch you later.